Hello everyone, welcome back to another video. Today we are going to be performing a von Neumann stability analysis of the expression or the model that we came up with in the last video that depicted how heat is going to dissipate throughout a bar when you have it starting at room temperature and then begin heating both ends of the bar. And what this is going to do is going to show us the limits of stability that we need in order for that model to actually calculate how that heat is going to dissipate as time goes on accurately. Because if you remember in the last video, whenever we made the time step more than half a second, things went a little wonky with our model and the temperatures just started shooting up and down all over the place, and it was obviously not an accurate representation of how that heat would dissipate over time. So today we're going to be doing some math to actually visualize and understand why that was the case, all right? So up here we have our partial differential equation that we had in I believe the second video. We found this equation in the second video to show how that temperature is going to change with respect to the position along the bar and as time goes on. And down here below, we actually have the answer to this partial differential equation. And we're not going to go into why this is the answer, because that would be a really long and complicated video. So we're just going to leave it as this. This is the answer to the partial differential equation right here. And within this partial differential equation, we have this k value right here. And all this k is, it is going to be based upon the boundary conditions that you would have at the end of the bars, whether or not it's insulated, whether or not you're only heating one end or both ends. So this is pretty much just dependent on what the conditions are at the boundaries of the bar, all right? And then we also have this imaginary number I over here in the first part of this expression. And pretty much the first step that we are going to do here is we are going to use this equation answer right here to substitute in for these t of j and n's, because we're going to want this to be all the temperature at the same position at the same time, because right here all of these temperatures are at different locations, with this being at a left position, a middle position, and a right position right here. So we are going to want to get this all in terms of the same position. All right, and in order to do that, we are pretty much just going to be substituting in these values in for this equation up here, all right? So in order to start off, we are going to start with the tj of n, the middle position. So we'll go ahead and do that now. All right, so in order to find our expression for the temperature at our middle position, we are going to go back to what we did at the start of the last video, when we split the position and the time into even fragments using some accounting numbers. And we said that our x was equal to j delta x. And all this is this x was the total length of the bar, and then we split that into a certain number of fragments. And in our case for the last video, we split it up into 20 fragments. And then this j was just used to account for which position at which fragment were at along the bar. And we did the same thing for the temperature using different variables. We used n delta t for that. And so pretty much all this temperature at this position is going to be, is we are going to substitute in our j delta x in for our x, and then our n delta t in for our t over here. So we'll go ahead and write that out. All right, and this is going to be our expression for tj of n. And now we have to look at t of j plus 1 and n, and then t of j minus 1 and n, all right? So over here, we'll start off with j plus 1. So this is going to be the temperature at the next position over in the fragments on the bar. So j plus 1 n. And pretty much all we are going to be doing here is we are going to be substituting in, instead of this right here, this is going to be j plus 1 instead of j. So we can go ahead and write that out. Like so. And then this temperature over here is not going to be changing at all. This side over here is going to be remaining the same since we are just moving on to the next position. This is the temperature. These are both being taken at the same time. The time is not being affected here. All right, so all that's really changing between this one and this one is that we have this factor right here. And then when we take this factor for j, this is just going to be the same exact value as our tj of n. And then when we have this factor equaling to 1, that's just going to be equal to ik delta x, right? Because that 1 isn't going to be changing. So we can just say that this is going to be equal to e to the ik times delta x being multiplied by tj of n. And then that's going to be the same exact thing for j minus 1, except this is going to be a negative exponent because we are subtracting by 1 instead of adding by 1, all right? So we can go ahead and erase this. Just make this e to the ik delta x. And then this will be multiplied by tjn. And then for the temperature at the position left of our initial position, again, this is also going to be taken at the same time, so this part over here is not going to be affected. This is going to be the same thing except with a negative exponent right here because we're going to subtracting 1 instead of adding 1. And there we go. These are going to be the expressions all in terms of tjn that we will go ahead and substitute in up here for all of our temperatures. And then I'll go ahead and write that up and erase this so we have a little bit more room to write it out, and we'll cut to then. Alright, so we've gone ahead and substituted in our expressions over here for the temperatures at the different positions, and they all had a common factor of T sub Jn, so we went ahead and factored that out, so it's looking a little bit more simple over here. And pretty much this is our expression over here for the temperature at the same position, but at different times. So this over here is going to give you the temperature at the next time fragment, because once again we split up the time into evenly spaced intervals, all right? So the next thing that we're going to want to do when trying to find the stability boundaries for our expression is we are going to need to do something with these imaginary numbers, right? Imaginaries are never good when you're trying to do some math, so we're going to have to find a way to get rid of those. And in order to do that, we're going to bring in Euler's law, which is pretty simple. All that is really saying is that e to the ix, this is going to be equal to, and pretty much all this x is all the other stuff within the exponent over here. So obviously the I is the imaginary number, but this x is representing k delta x, and then again k delta x over here, all right? So that is what this x is representing. And then this is going to be equal to cosine of x plus I times sine of x. And once again, this x within our trig functions over here is just the k delta x's, because that is what is being multiplied by the I within the exponent. And then over here, when you have e to the negative ix, that is also going to be equal to cosine of x, and it's going to be the same, except this time we are subtracting the I multiplied by sine x. And this is going to work out beautifully for us because, as you can see here, we have the same exact expressions here, except one is positive and one is negative. So we have one of these and one of these. And what that is going to do is that is going to cancel out the imaginaries over here, and we are just going to be left with 2 cosine x, right? And we also can't forget about the r out in front, obviously. So we can go ahead and use this out, and we'll go ahead and write out what that would end up being. Alright, so we have tjn plus 1. tjn is still out front. And then we have 2, because we're going to be adding them, 2r, and then this is going to be the cosine of k delta x. And then we also have this plus 1 minus 2r. And there you have it. This is going to be our new expression over here. This all right here, we know that this is going to have to be, this cannot be greater than 1. This expression that we have over here, everything on the right side besides our temperature, this is going to have to be less than 1. Because if this gets to be greater than 1, then our temperatures are going to be jumping up and down all over the place like we saw in that last video. So that is going to be our boundaries. The absolute value of this cannot be greater than 1. So it's going to have to be between -1 and 1. So we can go ahead and write that out now. We'll bring the 1 minus 2r out front. Alright, and then this is going to have to be less than or equal to 1, and also greater than or equal to -1 right here. Alright, and so what we can go ahead and start doing is we are going to be doing some pretty basic algebra using these greater than or less than. The first thing we can do is we can go ahead and subtract 1 from everything. That is going to make this into -2 and 0. And then that's also going to get rid of this 1 over here, leaving a common factor of 2r, which we can go ahead and bring out of this over here. And then this is going to be cosine k delta x minus 1, because this is going to be a -2r. And when we bring a 2r out of -2r, we're just going to be left with -1. And then this is going to have to be less than or equal to 0. Let's not forget our parentheses over here. All right. All right, so our next step is going to be looking at this cosine. We know that cosine can't be, it can't be more than 1 or less than -1 right here, which pretty much means that this is always going to be negative right here, because even if it was at its maximum value, that would be only equal to 1, and then we have a 1 right here, so that would become 0, all right? So we're not going to have to worry about our rightmost expression, because we know that due to this being a cosine function, this is always going to be negative right here, all right? So we don't have to worry about that. So we can just go ahead and look at our left parameter over here. All right, so our next step here is we are going to want to isolate r by itself. So what we can go ahead and do is divide this by 2, and then also divide it by cosine k delta x minus 1. So we'll go ahead and do that, and then we will also be flipping the signs so that we can make this positive over here. And then that will be this r becoming greater than will become a less than when we do that, all right? So when we do that, we're going to be able to factor out a 2 and divide that. So we're not going to have to worry about that. So we'll just go ahead and write everything out. So we're going to have 1 over 1, and then minus our cosine over here. Cosine k delta x. And then, of course, this is going to flip as well, because we flip the signs of everything else over here. So this less than is going to become a greater than. And there we go, we have r. And now that we have this, we can go ahead and look at the cosine values at its maximum and minimum, all right? So what's going to happen, the greatest that this cosine can be is 1, right? Because we know cosine can be anywhere from -1 to 1. So we'll go ahead and take a look at both examples when it's at its greatest and its most minimum. So at its maximum, this is going to be equal to 1. This is going to become 1 minus 1. and that turns this into 1 over 0, which we know is going to be somewhere near infinity, right? You can't calculate that out. So that would turn this, so when cosine k delta x is equal to 1, then this becomes infinity is greater than equal to r, right? That is what we can take out of this. And that doesn't really give us a whole lot, right? Because we know r is almost always going to be less than or equal to infinity, right? That's not really telling us anything substantial, right? So what we're going to do is we're going to look at when this is negative 1. And this is going to be a lot more useful for us. We're actually going to be able to gain something from this. So when cosine is equal to negative 1, this is going to become 1 minus a negative 1. And that's going to turn into addition. So this is going to become 1/2. All right, so when we have cosine equal to negative 1, we know that r is going to have to be less than or equal to 1/2, right? And which makes sense. This is the time step that we had in our last video. And once we made that time step greater than 1/2, things became a little wonky, right? Because we had earlier, when we had our equation in the last video, we said that this was equal to the heat diffusivity multiplied by the change in temperature, I believe, over the change in position squared, right? And then pretty much what we had here, we had constants for our alpha and our change in position. Those were both equal to 1, right? So those were canceled. And then our r value was pretty much just our time step, which we had as a half second. So it worked out all right. So our r was pretty much equal to the time step since everything else was equal to 1. And that's why whenever we went above 1/2, things became real wonky and started going up and down all over the place. So that is going to do it for today's video. I hope you guys learned something new and enjoyed. If you did, leave a like on the video and comment what you guys want to see next. Make sure to subscribe to the channel and enjoy the rest of your day.